In this video, we're going to look at topic 95, example 3, model with exponential functions. So before we get into that, I want to look at the concept of exponential growth and decay models right here. So exponential growth and exponential decay functions model quantities that increase or decrease by a fixed percent, right, to make sure you keep that in mind, fixed percent during each time period. Given an initial amount, which is A, let's highlight that, that's important. A is your initial amount, and the rate of increase or decrease, so the rate of increase or decrease are the amount A of t after t time periods is given by. And then we have both our exponential growth model and our exponential decay model. Notice that they are nearly identical. The only difference is going to be whether we are adding the rate or subtracting the rate. But the A value is still going to be that initial amount, so this A value here. Our t value, after t time periods, is going to remain the same, and then that value of 1 is going to remain the same. Some kind of limitations, we'll say, for A and B. A has to be greater than 0 in both cases. In exponential growth, B is going to be greater than 1. In exponential decay, B is going to be between 0 and 1. So keep that in mind. That'll come into play in the next example when we look at example 4 after this. And then your B value, we talked about exponential functions being y equals a times b to the x. Your B value is either determined by 1 plus r or 1 minus r, again, depending on whether it is a growth or a decay model. Okay, so yeah, that's pretty much it for that part. The growth or decay factor is equal to b, we just mentioned that, and the ratio is between two consecutive y values. Easy enough. So now let's get into the actual problem, 95.3, model with exponential functions. The population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% for the next 4 years. So we are asked first, what exponential function models the population of the city over that 4-year period? Since the population is growing, that's going to be a growth model. So that tells me that I want to use the formula A of t is equal to A times 1 plus r with that exponent of t there. All right, so now we just need to substitute some values in. They're not asking us for the actual population, so we're not going to calculate the population in this case. We are just going to set up the function itself. So A of t would be equal to A in this problem. Remember, A is your initial amount. So the initial amount is The initial amount is 4.6 million. So we're just going to put 4.6 for that. The 1 is a constant that remains the same, and we're going to add the rate of growth. All right, so the rate of growth is 1.3%. When you're substituting that in as your R value, it has to be the decimal version of your percentage. So we're not going to use 1.3%. We're going to convert that to a decimal, and we're going to use 0.013. And then t, this is kind of up for debate for this specific problem. They are giving us the specific time period of 4 years. So I'm going to put t as 4, but just remember that that 4 will change depending on the number of years that we're looking for. All right, so the exponential function modeling the 4-year period would have an exponent of 4. If it was 20 years, it'd be an exponent of 20. If it was 100 years, it'd be an exponent of 100. And then finally, what we should do is just clean up the inside parentheses. So let's add those two terms and change that to 1.013 and raise that to the 4th power. Again, you might want to have that 4 still as a t. That'll give you the function model for the entire kind of scenario. But since they're talking about a specific 4-year period, I'm going to put that 4 in there. All right, let's look at part B. If the population continues to grow at the same rate, what will the population be in 2040? So our formula would be 4.6 times 1.013 to the t power Well, in this case, t is going to be 30 because the population started in 2010. It is now 2040, so that's going to cover 30 years. I forgot to set the calculator up on the screen ahead of time, and it's too much work to pull this up while I do it. So what I'm going to do is just tell you that you would type this entire piece into the calculator just as it is, and then we're going to round to the second decimal place. So I'm not actually going to say equals. I'm going to say this is approximately, because we are rounding, this is approximately 6.78. So we would have 6.78 million as our solution or as our answer. All right, obviously this is approximate. It's not going to be exactly 6.78 million people, but based on this function model, that's what's going to happen. These type of problems are usually very direct. They're going to give you the initial amount. They'll give you the rate of increase or decrease. So you just need to decide whether it's a growth or decay model. And then depending on the number of periods or time period that they're asking you, will determine what you plug in for your t value. So that's it for example 3. You'll get some practice with that, and I think you'll find it to be quite simple.